Hello everyone, my name is Mohamed Beshr and I'll be beginning the first year of my PhD project titled Plasmon Mapping of SIRS Active Nanostructures for Prostate Cancer Detection using Scanning Probe Energy Loss Spectroscopy in October of this year. As I have not yet begun my project, I'll be introducing you to the idea behind my project and showcasing some preliminary measurements which have already been demonstrated experimentally by my project supervisor, Dr. Shane Murphy. This project aims to develop a novel technique, scanning probe energy loss spectroscopy, or SPELS, to directly image the plasmonic behavior of SIRS active substrates in order to optimize the Raman enhancement factor and consequently to lead to new nanostructure configurations suitable for cancer diagnostics. Raman spectroscopy is widely used as a detection tool of target molecules in forensic detection, environmental monitoring, and medical diagnostic applications such as cancer detection, where the ability to accurately detect low concentrations of molecules is crucial for early intervention. Conventional Raman spectroscopy suffers from low signal intensity as only about 1 photon in 10 to the 6 to 10 to the 8 is inelastically scattered, due to the low occurrence of inelastic light scattering. Surface-enhanced Raman spectroscopy, or SIRS, overcomes this issue by enhancing the electric fields of the incident and scattered light through resonant coupling with conduction electron oscillations in metal nanostructures such as gold and silver, called localized surface plasmon resonances, or LSPR, as is illustrated in this figure here. Molecules adsorbed on such structures experience significantly enhanced Raman scattering, improving sensitivity down to single molecule detection. The LSPR may be tuned by changing the nanostructure's size, shape, spacing, spatial arrangement, and composition using soft lithographic methods like nanospheric lithography. The behavior of these nanostructures is complex, and consequently, having an experimental technique capable of directly imaging LSPR is extremely useful for advancing the development of SIRS active substrates. The measurements will then be carried out on SIRS active substrates prepared using the nanospheric lithography method. This approach has been chosen due to the comparative ease of fabrication and lower cost, but also as it can produce patterns over a large area, making it easy to locate a suitable area for analysis with SPELS. Initially, a self-assembled monolayer, or SAM, of polymer nanospheres will be deposited onto a silicon surface covered by a native oxide. Then the water inner surface will be evaporated, leaving behind a dried mask of nanospheres. Metal-thin films such as gold and silver will then be deposited through the SAM mask. There are three different types of structures that can then be obtained. If a thick film is deposited, a continuous metal film is formed over the nanospheres, creating a film-on nanosphere structure as seen here. On the other hand, if instead a thin metal film is deposited, it will not form a continuous layer over the nanospheres, which can then be dissolved with a solvent such as toluene, leaving behind it an array of triangular nanoparticles where the film was deposited onto the substrate through the gaps between the nanospheres, as seen here. The third possible option is to deposit a thick film to obtain the film-on nanosphere structure, but to glue a second substrate on top of the gold film. If the nanospheres are dissolved and the two substrates are pulled apart like an Oreo cookie, it is possible that the gold film will remain stuck to the second substrate. This will look like an inverted version of the film on nanosphere structure, leaving behind an array of concave nanoballs, as presented here. The plasmon properties of each of these structures can be varied via the self-assembly method, or by controlling the nanosphere diameter and film thickness. The formation of plasmon hotspots can be enhanced by decorating the ordered nanosphere lithography arrays with additional nanoparticles obtained by ultra-thin film deposition or self-assembly methods. Plasmon hotspots can also be made by electrochemical roughening of the metal particles or physical deposition of size-selected clusters. The performance of the SIRS active substrates will be tested in parallel with their development by performing SIRS measurements on prostate cancer samples. The project pushes the boundaries of scanning tunneling microscopy, STM, capability. SPELS is a modification of STM, whereby the STM tip is used as a source of field-emitted electrons to probe the sample surface and the energy of the backscattered electrons recorded to obtain an energy loss spectrum. SPELS allows topographic and compositional information, including information on electronic excitations such as LSPR, to be acquired simultaneously over the same area of the sample. In SPELS, the tip is positioned 50 to 500 nanometers from the surface and negatively biased at 40 to 400 volts. With respect to the sample, electrons are field emitted from the tip as it is scanned across the surface, and they are scattered by the sample surface and collected by an electron detector. This electron detector is placed at a shallow angle to the surface as scattered electrons are deflected by the electric field between tip and sample, as illustrated here. This allows the energy spectrum of the backscattered electrons to be recorded. SPELS allows single-point spectroscopy measurements, mapping of a single spectroscopic feature, or measurement of energy loss spectra over a grid of points to produce a stack of spectroscopic images. An example can be seen here, where an energy loss spectrum was obtained from a 40 nanometer thick silver film on graphite by my project supervisor. A grid of SPELS measurements were taken across the surface to generate the spectrum, which is the sum of all spectra on the grid. The large peak at 0 electron volts, known as the 0-point peak, represents the elastically scattered electrons. The smaller peak at 3.6 electron volts, highlighted right here, is the Plasmon loss peak. By measuring the energy loss peaks due to LSPR excitation at each point in the image, it is possible to map the plasmon modes produced by the metal nanostructures. Direct plasmon mapping will enable tailoring of the nanostructures to improve the Raman enhancement factors and overall reproducibility. In order to produce a sample suitable for SPELS imaging with elemental contrast, the silver film was annealed at 640 degrees Celsius. This resulted in large 300 nanometer thick silver nanoislands separated by areas of bare graphite, such as the example shown in the STM image here. This was taken using a bias of -1 volts and a current of 1 nanoamp. A field emission image of the nanoisland was taken using a field emission bias of -148 volts and a current set point of 5 microamps. It is presented here alongside the STM image for comparison. Silver nanoisland here is reasonably well resolved, but the lateral and vertical resolutions decreases as the field emission bias increases, owing to the corresponding increase in the tip sample separation. The total backscattered electron image here was measured when the tip was located over the silver nanoisland. The total electron signal measured was found to be lower than that measured when the tip was over the graphite, so that the silver nanoisland appears darker. Finally, a plasmon loss image was obtained by normalizing the silver plasmon loss peak to the elastic peak at each grid point. This tells us how much plasmon loss there is at each point. On silver, the signal of plasmon loss peak is higher than when it's on bare graphite, and ideally on graphite it would be 0, generating black pixels, but there are some bright pixels which could have been due to silver being absorbed onto the graphite, giving a signal. The spatial distribution of the silver plasmon loss peak at 3.6 electron volts was mapped across the silver nanostructures with a resolution of around 50 nanometers. Due to the large size of the islands, it was not possible to detect any shifts in the LSPR to higher energies. Looking forward to starting my project very soon, our first step will be to start producing nanostructures using nanosphere lithography in order for us to start using SPELS to map the LSPR modes of small ligand-free nanoparticles with well-defined shape and homogeneous thickness. These measurements will be analogous to those performed on individual plasmonic nanoparticles using STEM eels. However, SPELS represents a much more accessible and lower cost method of doing this. These measurements will help to guide the development of SIRS active nanostructures that will then be tested for their selectivity and sensitivity in the detection of prostate cancer metabolites in blood plasma samples. Finally, the authors wish to acknowledge the kind donation of equipment from the University of Birmingham in the UK, and I would like to personally thank my supervisor Dr. Shane Murphy and my co-supervisors Dr. Aidan Mead and Dr. George Amarande for their continuous support and help. Thank you very much for listening, and I look forward to the Q&A session at the end of the week.